Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
The absolute upper limit of energetic events in the known universe is defined by the phenomenon of massive stellar death.
Right. When a star possessing significantly greater mass than standard main sequence stars exhausts its nuclear fuel, the hydrostatic equilibrium that maintained its structure for millions of years is catastrophically disrupted.
The inward gravitational pressure instantly overcomes the outward radiation pressure,
resulting in a core collapse.
Yes, and this collapse crushes the stellar core into an infinitely dense singularity. It forms a stellar mass black hole. The energy release metrics associated with this specific collapse mechanism represent the pinnacle of astrophysical energy generation.
The magnitude of this energy release requires a very precise quantitative framework to understand. During the formation of the black hole, a substantial fraction of the star's remaining outer envelope falls inward.
And the angular momentum of this collapsing material forms a hyperaccreting disk around the newly formed singularity.
Precisely. Through complex magnetohydrodynamic processes, specifically the winding of magnetic field lines and the extraction of rotational energy from the black hole itself, a significant portion of this infalling matter is redirected outward.
It doesn't all fall in.
No, it is accelerated to relativistic velocities, meaning it travels at a significant fraction of the speed of light, manifesting as bipolar jets ejecting from the rotational poles of the collapsing star.
The energy contained within these jets is categorized observationally as a gamma-ray burst. To contextualize the quantitative output, consider a standard G-type main sequence star, like the Sun.
Over its entire multi-billion-year lifespan, such a star will emit a specific calculable total volume of energy through continuous nuclear fusion.
But during the core collapse of a massive star, the high-energy radiation jets of a gamma-ray burst release an equivalent amount of energy within a temporal window of near seconds.
A total energy budget ranging from 10 to the power of 51 to 10 to the power of 54 ergs, discharged almost instantaneously.
The geometry of this discharge, however, dictates our observational capabilities. Gamma-ray bursts do not represent isotropic explosions.
No, they do not. In a standard supernova, the kinetic energy and radiation expand outward spherically. They distribute equally in all directions. Gamma-ray bursts, conversely, are highly collimated.
The energy is fiercely concentrated into narrow directional beams.
The opening angle of these jets is typically only a few degrees wide. The radiation is strictly confined along the polar axis of the progenitor star.
This high degree of collimation introduces a fundamental constraint, the observer angle limitation.
Because the emission is fundamentally directional, the initial highly energetic flash of high-energy gamma radiation is only detectable if the polar axis of the collapsing star happens to be pointed directly at Earth.
If the jet's trajectory deviates by even a few degrees from our line of sight.
The intense initial flash of the gamma-ray burst completely bypasses our space-based high-energy observatories. The primary emission is essentially beamed away from the observer.
This limitation establishes a foundational problem in high-energy astrophysics. The direct implication of collimated emission is that the vast majority of these immense cosmic explosions are completely invisible during their initial phase.
Statistical probability and simple solid angle geometry dictate that most jets will not intersect Earth's position.
Consequently, a massive population of the universe's most extreme energetic events occurs continuously without triggering any detectable initial flash on our monitoring instruments.
The catalog of observed gamma-ray bursts represents only a minute fraction of the total events occurring across the cosmos.
The kinetic energy of the jet, however, is not nullified simply because the primary radiation beam misses our detectors. The evolution of the event transitions into a new phase.
A phase dictated by the kinematics of an expanding shock front. When the highly collimated jet is initially launched, the internal material is moving at Lorentz factors, often exceeding 100.
And as this jet propagates outward, it inevitably encounters the circumstellar and interstellar medium. The sparse distribution of gas, primarily hydrogen, and dust particles occupying the space between stellar systems.
The interaction between the relativistic jet and the interstellar medium functions strictly according to the principles of momentum conservation and fluid dynamics.
As the accelerated material plows into the surrounding medium, it functions as a highly energetic piston.
It sweeps up the ambient gas. This drives a forward shock into the interstellar medium and a reverse shock back into the ejected material.
This collision generates a massive, highly energetic shock front.
The initial phase of this interaction is characterized by constant velocity, but as the swept-up mass of the interstellar medium begins to equal the initial rest mass of the ejecta divided by its initial Lorentz factor.
The deceleration process initiates.
Exactly. The deceleration dictates the subsequent morphological and spectral evolution of the emission.
As the shock front accumulates mass and encounters friction, the forward momentum of the jet is converted into thermal energy. This heats the swept-up electrons to relativistic speeds.
Simultaneously, the deceleration causes a reduction in the Lorentz factor. As the relativistic forward velocity decreases, the physical constraints that maintain the tight collimation of the jet weaken.
The jet begins to undergo lateral expansion.
The narrow beam widens, spreading outward to encompass a broader solid angle as it propagates through the interstellar medium.
This lateral spreading is coupled with a fundamental wavelength shift across the electromagnetic spectrum.
The emission mechanism at play is primarily synchrotron radiation. This is generated by relativistic electrons spiraling in the amplified magnetic fields behind the shock front.
Initially, when the shock velocity is at its absolute highest, the characteristic frequency of this synchrotron emission peaks in the highly energetic gamma and X-ray bands.
However, as the expanding shell of material decelerates and the internal thermal energy dissipates, the shock front cools.
The cooling process directly alters the spectral energy distribution. The peak of the emission spectrum shifts from the undetectable, highly focused gamma and X-ray wavelengths to broader, lower energy wavelengths.
Over a time scale of days to months, the emission shifts through the optical and infrared bands.
Eventually, as the deceleration continues over months and years, the primary observable emission from the expanding, widening shock front settles strictly into the radio wave end of the electromagnetic spectrum.
The specific observational signature produced by this sequence of events is classified within the literature as an orphan afterglow.
An orphan afterglow. It is defined as an expanding, slowly fading, long-lived radio transient originating from a massive stellar explosion whose initial, highly directional, high-energy gamma-ray flash was never witnessed by observers on Earth.
The afterglow is orphaned because the parent explosion was geometrically concealed from our vantage point. We are only detecting the delayed isotropic secondary emission produced by the decelerating shock front interacting with the interstellar medium.
Confirming the theoretical predictions of orphan afterglows has presented a severe historical difficulty for observational astronomy.
Standard afterglows are located by detecting the initial gamma-ray burst. That prompt emission provides precise spatial coordinates.
A trigger to point multi-wavelength telescopes at a specific region of the sky.
But searching for an orphan afterglow requires an untargeted approach. It necessitates scanning massive, unconstrained portions of the celestial sphere to identify faint, transient radio signals without any prior temporal or spatial data regarding the initial explosion.
Executing such a search requires observational apparatus designed for massive data throughput and wide field sensitivity.
The Australian SKA Array Pathfinder, designated ASKAP, represents exactly this class of instrumentation.
Located at the Inyaramana Ilgari Bandora Observatory in the radio-quiet environment of Western Australia. ASKAP is a highly advanced radio telescope array designed to map the sky at unprecedented speeds.
The architecture of ASKAP relies on the principles of interferometry, rather than utilizing a single monolithic parabolic reflector.
The array consists of 36 distinct antenna dishes, each measuring 12 meters in diameter. By linking these antennas and utilizing supercomputing facilities to correlate the signals, the array functions as a single synthesized telescope.
The resolving power is determined by the maximum distance between the antennas, known as the maximum baseline. The sensitivity is determined by the total collecting area of all 36 dishes combined.
The defining technological advancement of ASKAP is its implementation of phased array feeds, or PAFs.
Traditional radio telescopes utilize a single feed horn at the focal point. This provides a single pixel of observation.
The PAFs on ASKAP consist of a checkerboard array of dipole antennas, which allows the system to electronically form multiple simultaneous beams.
This expands the instantaneous field of view to 30 square degrees.
This methodology is critical for wide-field radio surveys. It enables the continuous monitoring of 1,000-square-degree regions of the sky to detect transients.
Astronomical sources that exhibit flux variations, appearing, changing, or vanishing over timescales of weeks or years.
The continuous monitoring capability of ASKAP yielded the detection of a specific anomaly, cataloged as ASKAP-J 005512255834.
During a comparative analysis of wide-field survey data, researchers identified a distinct radio source at these coordinates that was entirely absent in earlier observational epochs.
The source manifested rapidly. It presented a profound surge in radio frequency luminosity.
The energy output calculations for this specific transient are highly constrained. The data indicates that the source rapidly brightened, reaching a peak luminosity that released 10 to the power of 32 watts of energy strictly into the radio spectrum.
To frame this magnitude mathematically, the isotropic radioluminosity of ASKAP J005512255834 at its peak was equivalent to the combined radio frequency energy output of several billion standard main sequence stars.
The energy budget required to power this continuous emission is firmly in the regime of catastrophic stellar death or massive accretion events.
The diagnostic value of the anomaly lies heavily in the temporal and spectral behavior of its emission. The temporal evolution of an astronomical transient's brightness is tracked using a light curve.
The light curve for ASKAP J005512255834 demonstrated a definitive pattern beginning in 2022.
Following its initial rapid brightening to peak luminosity, the source did not exhibit subsequent flaring, plateauing, or rapid quenching.
Instead, it commenced a steady, continuous, and purely monotonic fade. The flux density decreased predictably without deviation.
The duration of this monotonic decay extended for over 1,000 days of continuous observation.
This specific temporal behavior provides a stringent filter against standard transient phenomena. Pulsars, for instance, display highly periodic rapid emission profiles.
Active stellar flares evolve rapidly over hours or days with significant stochastic variability.
Typical supernovae exhibit light curves that fade much more rapidly in the radio bands, often accompanied by distinct spectral shifts indicative of expanding stellar ejecta.
A singular, prolonged, 1,000-day, unvarying decay trajectory strongly isolates the underlying physical mechanism.
The decay profile conforms with high precision to the theoretical model of an orphan afterglow's expanding shock front.
As the shock front sweeps up interstellar mass and decelerates, the physical volume of the emitting region expands laterally.
The total thermal energy is distributed over an increasingly larger surface area, leading to a steady decrease in surface brightness.
The specific power law decline of the radio flux over the 1,000-day period perfectly matches the mathematical predictions for a decelerating relativistic jet viewed off-axis.
Where the lateral spreading of the jet gradually brings the emission into the observer's line of sight, just as the overall energy of the shock front is dissipating.
The physical model of the delayed cooled radio echo is further cemented by the absence of cross-spectrum data.
Upon identifying the radio transient, subsequent observation campaigns were executed using high-energy orbital platforms and ground-based optical observatories.
The objective was to locate any corresponding emission in the X-ray, ultraviolet, or visible light spectra.
These multi-wavelength observations failed to detect any counterpart. Deep upper limits were established, proving the source was entirely radio-dominant.
The absence of optical or X-ray emission is a critical diagnostic parameter. If the event were a standard core collapse supernova, a significant optical signature from the radioactive decay of heavy elements synthesized in the explosion would be expected.
If the central engine, the newly formed black hole, were actively accreting matter and driving new outflows at the time of detection, hard X-ray emission would be present.
The complete lack of high-energy and visible light confirms that the prompt, highly energetic phase of the event concluded long before detection.
The anomaly represents the isolated, cooled remnants of a shock front that is now only capable of producing low-frequency radio waves.
Analyzing the nature of the explosion requires establishing its spatial context. The initial observations utilized spectroscopic analysis to determine the cosmological distance of the host environment.
The measured redshift of the host galaxy is Z equals 0.1.
Utilizing standard cosmological parameters for the expansion of the universe, a redshift of 0.1 translates to a luminosity distance of approximately 460 megaparsecs.
This places the origin of the event roughly 1.7 billion light-years from Earth.
The characteristics of the host galaxy provide further parameters regarding the progenitor of the explosion. The galaxy located at redshift 0.1 is classified as small, but possessing a high surface brightness.
Morphologically, it presents an irregular structure. It lacks the defined spiral arms or smooth elliptical distribution seen in older, dynamically relaxed galaxies.
Such irregular morphology is heavily correlated with ongoing disruptive gravitational interactions or the accretion of intergalactic gas.
The irregular structure indicates a specific galactic environment, a region of active, rapid star formation.
The galaxy is characterized by a high specific star formation rate. Environments producing massive quantities of newly formed stars are statistically the most probable locations for extreme stellar phenomena.
Massive stars, specifically the O and B type main sequence stars required to trigger gamma ray bursts, possess extremely short lifespans, often only a few million years.
Consequently, massive stellar death and violent disruption events are concentrated in these chaotic starburst environments.
The astrometric positioning of the transient within this host galaxy introduces the next layer of complexity.
High-resolution imaging was required to determine the exact spatial coordinates of the radio emission relative to the galactic structure.
The data reveals that the explosion is located off-nuclear.
It is situated significantly away from the dynamical center of the host galaxy, exhibiting a projected offset of several kiloparsecs from the galactic core.
An off-nuclear location immediately alters the diagnostic probabilities. The center of a galaxy is the primary habitat for supermassive black holes.
Had the emission originated precisely from the nucleus, the event could be modeled as a flare from an active galactic nucleus or a transient accretion event onto a supermassive black hole.
Because the event is strictly off-nuclear, the localized environment must be examined. The emission coordinates map directly to a highly compact star-forming region,
Categorized potentially as a nuclear star cluster, but one that is orbiting in the galactic periphery rather than residing at the center.
The precision required to state these localized coordinates relies on rigorous corroborative verification.
In observational astrophysics, localized claims regarding transient events necessitate multi-facility confirmation to eliminate instrumental artifacts or atmospheric interference.
To secure the spatial data, the research team utilized the Magellan Telescope Array in Chile.
The optical capabilities of the Magellan facility captured the precise morphology of the irregular host galaxy and isolated the specific compact star cluster, acting as the progenitor environment.
Concurrently, independent verification of the radio transient itself was obtained using the Giant Metro-Wave Radio Telescope, or GMRT, situated in India.
The GMRT observations were conducted at different observing frequencies than ASCAP, specifically to measure the spectral index of the radio emission.
This independent detection confirmed the exact spatial coordinates, verified the persistent nature of the transient, and validated the non-thermal synchrotron nature of the radiation.
The dataset is therefore robust. It confirms a multi-year radio-exclusive transient fading steadily within an off-nuclear massive star cluster located 1.7 billion light-years away.
The established parameters demand a thorough differential diagnosis.
The scientific method requires the analytical elimination of alternative astrophysical sources before confirming the presence of an orphan afterglow.
The persistent, non-repeating, and purely radio-dominant nature of the light curve serves as the primary mechanism for this elimination.
Standard stellar activity, such as coronal mass ejections from active dwarf stars, is easily dismissed due to the sheer luminosity difference, orders of magnitude below 10 to the 32 watts.
And the timescale of the flare, which typically resolves in days, not years.
Similarly, the hypothesis of a highly magnetized rotating neutron star, or pulsar, is eliminated.
While pulsars are strong radio emitters, their emission is characterized by rapid, highly regular pulses resulting from their rotation, and their flux levels remain relatively stable over long timescales, rather than exhibiting a strict, continuous, multi-year decline.
Furthermore, standard core collapse supernovae are ruled out. As established, the expected multi-wavelength signature, specifically the prominent optical peak driven by radioactive nickel-56 decay, is absent.
The radio emission from standard supernovae also evolves differently, typically peaking much earlier and fading faster than the 1,000-day monotonic profile observed in ASCAP J005512255834.
Having analytically eliminated standard variables, the differential diagnosis forces an examination of alternative high-energy mechanisms capable of producing this specific set of observational constraints.
The data profile leaves only one mathematically and physically viable alternative to the orphan afterglow hypothesis.
The singular alternative explanation is that the transient represents a tidal disruption event, specifically one triggered by an intermediate mass black hole.
Evaluating this alternative requires defining the mechanisms of an intermediate mass black hole, or IMBH. The astrophysical census of black holes is heavily populated at two distinct extremes.
Stellar mass black holes, the remnants of single massive stars, possess masses generally ranging from 5 to 100 times the mass of the Sun.
Conversely, supermassive black holes residing at galactic nuclei possess masses ranging from hundreds of thousands to billions of solar masses.
The intermediate mass range, spanning from roughly 100 to 100,000 solar masses, represents a critical evolutionary missing link.
Identifying an IMBH is notoriously complex. Because they lack the extreme mass required to continuously accrete massive amounts of surrounding gas and dominate the dynamics of an entire galactic core, they remain largely quiescent and optically dark.
They do not produce the massive accretion disks and relativistic jets characteristic of active galactic nuclei.
Detecting them relies predominantly on rare transient events, specifically when a secondary object directly interacts with the black hole's event horizon.
The interaction capable of highlighting an IMBH is the tidal disruption event. A TDE occurs when a star's orbital trajectory carries it within the tidal disruption radius of a black hole.
At this proximity, the gravitational gradient across the diameter of the star becomes immense. The tidal forces, the difference in gravitational pull between the near side and the far side of the star, overcome the star's own internal self-gravity.
The star undergoes catastrophic structural failure. The physical destruction of the star follows complex fluid dynamics.
The stellar material is subjected to extreme shear forces, stretching the star into a continuous stream of stellar plasma, a process formally detailed in the literature as spaghettification.
The star is entirely dismantled. Half of the stellar debris is ejected entirely from the system at high velocities,
while the remaining material remains gravitationally bound, falling back toward the black hole along highly eccentric orbital trajectories.
As the bound material returns to the pericenter of its orbit, the streams intersect.
The resulting shock heating causes the material to lose orbital energy and circularize, rapidly forming a temporary, highly luminous accretion disk around the black hole.
This sudden influx of mass triggers an intense flare of electromagnetic radiation.
In specific orientations and under specific magnetic field conditions, the rapid accretion can also launch a relativistic jet outward from the black hole's poles. Analogous to the jet launched during a gamma ray burst, albeit driven by the sudden consumption of a star rather than a core collapse.
The parameters of a TDE provide a strong theoretical fit for the anomaly when aligned with the spatial context.
The location of the transient is off-nuclear, within a highly compact star-forming region or nuclear star cluster located in the galactic periphery.
The dense stellar packing within such clusters is the exact predicted habitat for an elusive intermediate mass black hole.
High stellar densities promote runaway stellar collisions and dynamical friction, mechanisms theorized to merge multiple stellar mass black holes into a single IMBH over cosmological timescales.
If an IMBH resides within this dense cluster, the probability of a star entering its tidal disruption radius is elevated.
If a TDE occurred, the subsequent jet launched from the accreting stellar debris would propagate outward, slamming into the dense circumstellar medium of the star cluster.
This interaction would produce a decelerating shock front, mirroring the exact kinematics of the orphan afterglow.
The expanding shock front would cool, producing the specific 1,000-day monotonic fading radial light curve observed by SKA.
However, the TDE hypothesis introduces a significant observational complication regarding cross-spectrum emission.
Traditionally, tidal disruption events are primarily identified by their brilliant flares in optical, ultraviolet, and X-ray wavelengths.
The superheated accretion disk formed by the destroyed star radiates intensely across the high-energy spectrum.
A radio wavelength exclusive TDE, an event generating a massive 10 to the 32-watt radio afterglow without any corresponding high-energy or visible light detection, is an extraordinarily rare occurrence.
Reconciling the lack of optical and X-ray data with a TDE requires highly specific environmental or geometric conditions.
Deep, dense dust lanes within the nuclear star cluster could theoretically obscure the optical and ultraviolet light from the accretion disk, absorbing the high-frequency radiation while allowing the longer radio wavelengths from the expanding jet to pass through unattenuated.
Alternatively, if the TDE launched a highly collimated jet that was pointed away from Earth, the observer angle limitation would apply exactly as it does for a gamma ray burst.
We would miss the prompt high-energy flare and only detect the radio emission as the jet decelerated, widened, and entered our line of sight.
The implications of the data present a profound dichotomy. The mathematical modeling robustly supports two distinct scenarios.
The transient ASKAP J00Psi5122555834 is either the most precisely recorded example of an orphan gamma ray burst afterglow, validating decades of shock front kinematics and proving the existence of an off-axis jet decelerating in the interstellar medium.
Or it represents the first ever confirmed radio-exclusive detection of an intermediate mass black hole actively undergoing a tidal disruption event within a peripheral star cluster.
In either scenario, the data necessitates an epistemological shift in astrophysics.
For the entirety of observational astronomy, the detection of the universe's most violent events has been heavily biased toward prompt emission.
Observational methodologies relied entirely on detecting the initial highly luminous flash aligned directly with our instruments. We mapped the energetic universe based exclusively on events that effectively announced themselves across the cosmos.
The detection of ASKAP J005512255834 dismantles this paradigm. It proves that comprehensive study of extreme cosmic events is no longer restricted to prompt high-energy flashes aligned with Earth.
The deployment of wide-field high-sensitivity radio arrays allows for the systemic detection of the delayed echoes produced by these events.
The kinetic energy injected into the interstellar medium remains detectable long after the primary emission has ceased or bypassed us.
The final implication lies in the mathematical reality of this methodology. Given that standard high-energy jets are collimated to within a few degrees, solid angle calculation dictates that upwards of 98 to 99% of all massive stellar collapses and relativistic TDEs are oriented away from our line of sight.
Therefore, the vast, unseen bulk of the cosmos's most extreme energetic history is not missing. It is currently drifting through the vacuum as silent, slowly expanding radio shock fronts. You are challenged to consider how existing astrophysical models must be recalibrated now that technology permits the systematic mapping of this massive, invisible population of cosmic echoes.